All right, welcome everyone. Glad to see you guys in person. So today we're going to go through and hopefully finish the review lecture I have on basic linear algebra. So I'm assuming you guys have seen this before, although not all of it might be in front of your mind. So I'll be, this class and other classes, just calling on your names randomly and asking you some questions. If you don't know the answer, it's not a big deal. I'm really just checking for attendance, not correctness. But it also, I've found it helps to keep students a bit on their toes. So anyway, let's get started. So we might say, first, why are we using linear algebra? Basically, it's a really good way of notating and combining and communicating about situations where we have a number of different variables operating together. And as a simple example, we might have two variables, x1 and x2, and the way that they're connecting together is that there's two linear systems of equations. And so we might first say, well, how can we write this as in terms of matrices and vectors? So let me just call on someone randomly. Is Shivani Rajagopal here?
Yes.
Okay, yeah. So how could we write this in terms of, let's say, a matrix and a vector equals another vector? See a way of doing that?
So I guess you could split it. So you could set it equal to 3 on the top and 4 on the bottom, on the right.
Okay.
And then to split the others, I guess you would take the coefficients, so like 5 and 2 in the first bracket.
Okay.
And then -4 and 1.
Good.
And then it's being multiplied by x1 and x2, so.
Exactly. Yeah, that's exactly how we do it. And and basically the main idea that we're using there is how matrix multiplication works. And so the way that it works is that basically 5 times x1 plus 2 times x2 equals 3. And then -4 times x1 plus 1 times x2 equals 4. So that's always how we do it. We kind of take this times this, where when we do this times this, what we mean is really the first times the first plus the second times the second and so on. And then we do this times this to give us this. And we'll see a lot of that going forward in these notes. So that's one way we can do it. We can also describe this algebraically by giving each of these things names. So we could call this first thing capital A, a matrix, in which case that A would be 5, 2, -4, 1. And then X, the vector, would be x1 and x2. And B, this vector, would be 3, 4. And in that case, we would have those quantities would obey this equation. And so now one thing we could do once we have that equation is if you want to know what are the values of x1 and x2 that solve that system of equations, we could use the concept of matrix inverse. So the idea is we start with the equation that we have from above, and if I say this quantity equals this quantity, then that means I can perform the same operation on both quantities and they'll still be equal. And so the operation I'm going to apply is I'm going to multiply on the left both quantities by A inverse. A inverse denotes the inverse of this matrix A. We'll talk about that in a few slides. But the reason we do this is that A inverse times A, it kind of they cancel each other out, leaving X alone. And once we've done that, now we have finally an expression for X as the matrix A inverse times the vector B. And from that, we could directly compute the values of the coefficients x1 and x2. So that's just sort of one motivation. But really for us, this is going to be the way that we describe things, because when you look at this equation, you can see this is a lot more concise and interpretable than something like this. This is kind of messy. There's a lot of stuff going on. It's kind of distracting. But here you can kind of, once you look at this, you can immediately start to make some interpretations about what's going on depending on the properties of some of these quantities. Okay, so that's sort of a motivation. And so let's just begin by talking about the notation that I'm going to use in this class. So whenever we see a non-bolded font on some math quantity, that means that it's going to be a scalar. So examples of this would be like a little c or a big C. Those might be the scalars 1. Now, if we have bold lowercase, that is always going to mean a column vector in this class. So for example, here is the bold lowerface, and here I'm saying this is a column vector, which is a matrix of, in this case, 3 by 1. And now you can notice that the terms inside are not bold. They're each scalars. And I want to emphasize this is always going to be a column vector. So if you ever want to have a quantity that is going to be a row vector, we'll need to transpose this, as we'll see below. Now, if you see a bold uppercase quantity, that will mean a matrix. And so in this example, we have bold uppercase A, and that's this matrix, which is generally some array of numbers where you have more than one element in each row, more than one element in each column. But of course, this is a special case of a matrix, a vector, and even these scalars are special cases of matrices. But usually when we talk about matrices, they have some structure like that. Okay, now if you want to talk about what is in the ith row and jth column of a matrix, we're going to use this notation with the square brackets and the subscript ij. Now, in some cases, we'll use, if we're talking about matrix A, we'll use a little aij to represent the ith row and jth column. But that might not always be true. That might be true in some cases, but not always. So just, if you really want to say, like, I have something and I'm going to look at the ith row, jth column, we're going to use this square bracket notation. And we have the transpose operator. The transpose operator is something that just basically swaps rows and columns. So if we start with this matrix here that has 2 rows and 3 columns, and we transpose it, what do we get? Let me ask this to Emmanuel Temesgen. Yes. What do you think? What do we get?
Yeah, we'll turn into this is a 3 by 2, so we'll be 2 by 2.
Okay, yes, so, and what's in the first row?
A11,
Mm-hmm.
A21.
Exactly. Okay. And then the next row here is the same as the column, the second column, and the third row here is the transpose of the third column. Okay, so yeah, basically this got moved here, this got moved here, this got moved here. So that's the notion of the transpose. Now there's a couple important properties of the transpose. So as for the first one, let's see, is Jun G here, X-I-E? No. What about, I don't know how to pronounce this, Q-I-Z-H-E, Zhu, X-U. Okay, yeah, so what do we get if I transpose a matrix A and then transpose it again?
And we get A.
We just get A, exactly. So here we have A. Now when I write things on these slides, because it's hard for me to make a boldface notation, I'm going to use an underline. That is going to mean the same thing as boldface. And that is what I suggest that you do, especially on an exam. There can be very different meanings to a boldface A and a non-boldface A. And if you don't notationally distinguish them, by making one look different than the other, I have no way of knowing which of those two things you're talking about. And I can't give you full credit. Okay, so it's really important to do something like this, at least in this class. Outside this class, you can do whatever you want, but I would really like you guys, when you have a vector or matrix, to distinguish it with an underline. so we can keep these things separate. It makes everything a lot easier to understand. Okay, so that's one property. Here's another property. If I have A times B, and we'll talk about matrix multiplication in just a moment, and if I transpose that, let's see, what do we get? Is Jerem Christensen here? No. What about James Fitzsimmons? Yeah.
You get B transpose times A transpose.
Exactly. You get B transpose times A transpose. So the key thing is that they individually get transposed, but their order gets reversed. Okay. Excellent. So moving on to different ways of writing matrices and vectors. So here we have a matrix, boldface A, 2 rows, 3 columns. Sometimes we might want to describe that matrix in terms of its column vectors. So we want to give this thing a name. Since this is a column vector, we're going to give it a name which is bold lowerface a. And since it's the first column in this sequence of columns, we can call it A sub 1. Likewise, we can call this here A sub 2, and this one here A sub 3. Okay, so in other words, A sub 1 we said is A11, A21, vector A2 is A12, A22, and vector A3 is A13, A23. Okay. Another example is if I have this 2 by 3 matrix, maybe I want to describe it in terms of row vectors. So we said that whenever you have this bold lowercase alone, it must be a column vector. Whenever you see that sort of thing with a transpose, it must be a row vector. So here we have one row vector, here we have another row vector, and notice that those row vectors are exactly the row vectors in this matrix A. So then how can I write matrix A in terms of those vectors? Let me ask this to Camden Majors. Is Camden here?
So we put A sub 1 transpose on top and A sub 2 transpose on the bottom.
Exactly. So we have that. So just in this case, keep in mind that that this is like an entire row, this is an entire row. Even though it's just one little, A thing, it's really an entire row. Okay, any questions? Is everybody good so far? Okay. Okay, let's talk about matrix multiplication. So if we have two matrices, capital A and capital B, we can multiply them as long as their dimensions match. And what we need to match is that we need that the number of rows in A, which is given by, the number of columns in A must match the number of rows in B. Okay. And if those two things match, then I can do A times B. And let's just say that this gives us a matrix C. The question is then, what is in C? We can write it using this summation. It might be a little bit easier for me to draw what I mean, just visualize it. I find these visualizations to be super useful. I think most students do the same. So here I have matrix A. Let's just visualize it by a big square thing. And it doesn't need to be square necessarily. It could be tall or wide. So what we're going to do, remember that the way the matrix multiplication works is, let me make a little bit more room. And I'll put C over here. Okay, so remember that to get the top left column of C, you would take the first row of A and you would multiply that by the first column of B. And when I say multiply that, what I mean is you take the first element there times the first here, plus the second times the second, plus the third times the third, dot, 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 till the end times the end. And in doing that, you can see that the number of elements along the columns of A must match the number of elements along the rows of B, and that's why these numbers must match. If they do not match, you cannot do this multiplication. It would be illegal. Okay, but in this case, we'll say that they do match. And now coming back again to this picture here, if I want to say what is in the ith row of C and the jth column, so that is this. That's the ith row, jth column element of C. That's some element in the middle there. What I'm going to need to do is I'm going to need to look at this row of A, which is the ith row, and I'm going to multiply that times the jth column of B. So in other words, I'm going to do this number times this number, first times first plus second times second, dot, 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 times last. And so one way I can sort of annotate that is I can draw an arrow here, taking me over some new index that I can call whatever I want. In this equation, I happen to call it k. But k will be the index that I can think of going across the columns of A, and k is also the index that I can think of that's coming down the rows of B. And so now with this picture, or maybe we can even add some detail here. So we're looking at this element of the C matrix. You can see why this equation holds. So we're saying the ith row, jth column of C. I take the elements in the ith row of A, all of these guys, and I take the elements in the jth column of B, all of those, and I do, use by incrementing k from 1 to p, I do first times first plus second times second, and so on, last times last. And so that's where this equation comes from. All right, is everybody good with this? Is this ringing some bells from long ago? Okay, so this is the sort of stuff, this is like super basic linear algebra. If you look at like a textbook on linear algebra, this is probably, like in the first 10 pages, and there's probably like a half page on it, and then the rest of the book is on more advanced topics. So we don't necessarily need a lot of advanced topics for this course, but we need to be really good at the basic stuff so that when you see equations, you can interpret them, you know what's going on. They don't look like just weird Greek letters to you. So this kind of stuff, just being able to do this is what I care about. Okay, so now we can do another example of matrix multiplication here. So what I'm going to do is to get this element, again, I'm going to do this times this plus this times this. So that is going to be AE plus BR. Give myself more space. And then to get the next element here, it's going to be AF plus BS. And then to get the top right, it's going to be AG plus BT. Moving on to the bottom, CE plus DR, CF plus DS, CG plus DT. Okay, so sorry, my handwriting is not perfect there. Is everybody good with this example, the general concept? Okay. All right, so something to keep in mind when we do matrix multiplication is that the order matters. Matrix multiplication does not commute like scalar multiplication does. So A times B is not the same as B times A. It might have completely different dimensions depending on the order of the multiplication. Okay. So let's talk now about some special cases of this idea. The first special case is called the inner product. It's an operation that is performed on two vectors, in this case A and B, And these vectors, for an inner product, you always have the first in row form. That was what happens with this transpose. The second in column form, because there's no transpose. And what do we get? Let me ask this to Sunny Agrawal. Sunny here?
It would be like summation of all, like, AI, DI.
Okay, so we'll do an I. The summation goes from I what to what? 1 to n. And then we're going to have AI, BI is what you said. Exactly. Yeah, when you write your sums, make sure, especially if it's on a test, like, write the whole thing so that I know that you know what's going on. If you write a sum without any quantities at all around it, I don't really know what you're summing over. Okay. So if we have the special case where you do this inner product and you find that the value you get is 0, when that happens, we say that those two vectors are orthogonal. Geometrically, that's like if they're at right angles. So that's exactly what happens when A and B are two-dimensional vectors, and you think of the 2 points, or the 2 entries in those vectors as points on a plane. Then in that case, when they're orthogonal, you really do have 2 lines at right angles. But it turns out that the same thing also happens in 3 dimensions. You can have, in 3 dimensions, 2 different lines, and there's all sorts of ways that those lines could be perpendicular to each other. And actually the same thing happens in higher dimensions, 4, 5, 6, and so on. It's hard for us humans to visualize beyond 3 dimensions, but what's nice is that the geometry is the same for any arbitrarily high finite dimension. Whatever intuitions you have from 2 and 3 dimensions, they hold over in higher dimensions. So that's what's great about it. All you have to do is visualize in 2, 3 dimensions, and you can understand what happens in higher dimensions, like this would be n dimensions. Okay, so that's the inner product. The outer product is what happens when you take the first as a column and the second as a row. So if this is a column and this is a row and you multiply them, now you get an entire matrix. As you can see, this is very different than this is a scalar, right? You could say this is in the set of real numbers. Down below, we have something in the set of n by n matrices. Totally different, and all we did is change the order of the multiplication between those 2 quantities. So that's just an example of this. Okay, so we have inner products, outer products. And now kind of coming back to mixtures of matrices and vectors, there's lots of ways that we can form matrix products using vectors. So here's one way to do it. So this matrix A is given over here, and each of these vectors, we don't really know how tall they are. They could be scalars, possibly, or they could be, very tall. They could be way more than 3 elements tall. It doesn't really matter. As long as they match this dimension, as long as this dimension matches this dimension, we can do this multiplication. And so now the question is, how do we write this as a sum? How do we write this thing in terms of the little a's and b's? So let me ask this to Grant Merka.
You would just take the first element of the A vector and then multiply it by the first element of B.
We actually, so what I'm looking for is not breaking up the A vector at all. I just want the A vector, the first A vector to stay as it is.
Would you just combine them together, like A1, B1 transpose the first element?
Yes, exactly. That's what's sort of cool about this, is we're going to have, we can do it. So even though these are not scalars, but they're vectors, the same general idea that we saw over here works. We just replace that with whatever size quantity we have. So in this case, we have a column vector. Here we have a row vector. this is an entire matrix. Because that AI BI transpose is exactly of this form. So what this is saying is that this whole matrix is like a sum of three different matrices. A1, B1 transpose is the first one. A2, B2 transpose is the second one. A2, B2, so A3, B3 transpose is the third one. Okay, so this is one way of writing it. Is everybody good on that? Okay, now let's say that B1 is actually the first column of B. Here B1 was the first row. Now it's the first column, and now A1 transpose is the first row of A. So in this case, can we write this with, how do we write this second case without any big AB, just with the small ones? So let me ask this to Connor McKenna. Is Connor here?
So would you take, you have like a 3 by 3 matrix, A1 transpose times B1, and then below that A2 transpose times B1?
Exactly. That's exactly what we do. I won't fill in all the entries. Actually, sorry. Let's back up. Okay, so to get the first row here, we want to take this times this would be the first element, this times this would be the second, this times this would be the third. So the second would be A1 transpose B1, and the third is A1 transpose B3. Now, to get the second row, we would take A2 transpose times B1 for the first element. A2 transpose B2 for the second, and so on. Okay, is everybody good with that? So at sort of the macro level, this looks like an outer product. But when you zoom in, each of these guys are actually inner products between pairs of vectors. What about this, where we have A just as an entire matrix and we've split B into 3 individual columns? So let's see, is Fayaz Jamil here?
A times B1, A times B1.
Okay, so A times B1. What is that thing?
It's gonna be a matrix.
Is it a column or a vector or a matrix? Let's draw a little picture. So A is a matrix, B1 is a column vector. What shape does this have?
Matrix.
It's this times this gives us an element there, right? Then this times this gives us another element below it. Then this times this gives us another element below that, and that's all. Okay, so it's a column vector. So really this is the first column in this matrix. So let's then put it as the first column. And so now what's the second column in the matrix? A times B2, exactly. And finally, A times B3. Right. Good. And then we have one more. So how can we write this last one? Let me ask this to Hassan Saeed. Is Hassan here? Oh, yeah, there you are.
We just have it as a row.
Okay, so what's a row exactly?
So you just have it like diagonal, so you have like A1 transpose B, A2 transpose B.
Okay, so let's talk about this. We have A1 transpose B. Now, what is, oh, sorry, I forgot my underlines here. So what is the shape of A1 transpose B? Is it a column, row, scalar, vector?
Would it be a column?
So A1 transpose must be a row, right? And then we have a matrix, we'll assume B is a matrix. So when I do that, what do I get?
You get a column, right?
So let's think about this. So you have this times this gives you one element here. And then when I do this times this, it's to the right of it, another element. Right? So finally at the end of the day, what do we get? A row, exactly. So this thing here is actually a row. So that is going to be the first row of this big matrix. And below it, we're going to get the next row. A2 transpose B, and below that, A3 transpose B. So when you look at quantities and you wonder about their shape, maybe one way to think about it is that the inner dimensions, meaning the number of columns in A and rows in B, those things vanish when you do the multiplication. What remains is how many rows in A, that is how many rows are in this, and how many columns in B is how many columns are in this. The inner dimensions, they vanish as part of matrix multiplication. Like coming back to this equation, in this case, K is the inner dimension. I do a sum over K, and once I execute that sum, there is no more Ks. Ks are gone, right? But I still do have I's and J's active. I can say which I is like, which row of A am I talking about? And J is which row of B am I talking about? But the K is something that vanishes when we do that summation.
So what about that rule about the number of columns in A must match the number of rows in B?
Exactly.
So in the previous question that you asked,
Yes.
where you know that you have a matrix A, right? And since those are bold letters as well, that's also a matrix just in a different form, right? Like symbolized.
A is a matrix. This big A is a matrix. This big B is a matrix. I'm assuming that the multiplication is legal,
Okay.
and otherwise it would be kind of silly for me to write it. So assuming that it's legal, that implies that the number of columns in A must match the number of rows in B. Otherwise, we can't even do that multiplication. Yeah. So that's always a good assumption. On a homework or the first exam, I could give you, I could write down something like, do this multiplication, or say if it's illegal, And in this case, you'd say, oh, there's a mismatch. This has one column, this has 3 rows. I can't do that. That's an illegal multiplication. So instead of writing a number, you'd say, this is illegal. Yeah. But yeah, assuming that we will all master that concept, moving forward, we'll just assume we're writing things down that are legal and we won't have to really worry about it. Okay. Good. Any questions on what we've done on this page? So yeah, we'll be doing a lot of this stuff just because it helps. Like this stuff just happens as we talk about machine learning. We get things that we need to explain, and they take forms like this. Okay. All right. Let's move on to talk about a few special matrices. First kind of special matrix is a diagonal matrix. And when we say that a matrix is diagonal, it means that on the diagonal, you have possibly non-zero entries, but off the diagonal, you have all zeros. So, for example, you might have something like D1, D2, D3. Those are all numbers that might be non-zero. But then as you look off that main diagonal, you have all zeros. So that would be an example of a diagonal matrix. And because they show up a lot, we might just come up with this notation. Diag of D1 through Dn would be a matrix that is n by n, and along that main diagonal, you have those n numbers. And here's another way we could write it, that when you look at the ith row and jth column of D, If I equals D, which means you're on the main diagonal, then you get DI. But if I is not equal to D, sorry, if I is not equal to J, that means you're somewhere off the main diagonal, it's always going to be 0. Okay, next, identity matrix is a special matrix, which is a diagonal matrix, but it has 1s everywhere. So, and we always give that the name capital I. So here would be the 3 by 3 identity matrix. And the identity matrix is very special because multiplying by it does nothing. It's completely transparent. And that pertains to multiplying on the left or on the right. So if I have a matrix A and I multiply on the right by identity, I just get A. If I have a matrix B and I multiply on the left by identity, I just get the matrix B. And that happens for every A and B. In writing these equations, I'm assuming that the size of the identity, matches, is appropriate for the multiplication we're doing. Okay, so that's a diagonal matrix, identity matrix. Symmetric matrices are matrices where the upper right and the lower left are mirror images. Another way to say it is that they're invariant to transposition. If you swap the rows and columns, nothing happens. So just as one example, we can have a matrix like, let's see, what was my example here? I had a very simple example. Okay. So in this, we have, the main diagonal can be anything in a symmetric matrix, but what's important is that what's below and above are mirror images. So 2 and 2. So if I transpose this, this would become the first row, but as you can see, it's already the first row. Nothing happens. So A is equal to A transpose. Okay. So then we have another important kind of matrix called an orthogonal matrix. An orthogonal matrix is a matrix which has orthonormal rows and columns. What is orthonormal? It's where the rows are orthogonal to each other, meaning right angles to each other. And we also have a case where each of the rows and columns are normalized in a certain way. We haven't talked about the norm yet, but it's going to be that they're normalized so that the Euclidean norm is 1. And when you have that, so this is sort of an encapsulation of that idea. So if you look at different I and j, because they're orthogonal, their inner product gives you 0 as a definition of orthogonality. And if I and j are the same, this thing ends up being the Euclidean norm, as we'll talk about in a moment, and that gives you the value of 1 for all the i's and j's. And because of this property, maybe we can visualize this a bit. If I take U transpose and U, for example, and I look at these are the columns that we're talking about over here. These are the UIs. And because I've transposed it on the left, those same columns manifest as rows here. And now when you look at this product and you say, okay, what do I find in the top right entry? That would be this times this. And we've said that those things are normalized so that you get 1. And then you say, what about this entry, top right entry? That would be this times this. But we said that those two vectors, they're different vectors, they are orthogonal. So that's why we're going to get a 0 here. And similar happens there and there. You end up getting the identity matrix. it turns out that all the stuff that we said down here, this happens for rows or columns. When you have an orthogonal matrix. So all those same things apply when I look at U transpose U. And so one interesting consequence is that U inverse is what? Let me ask this to Andrew Noonan. Is Andrew here? No? Okay. What about Fazet Muselli? Yes? Yeah, okay. Yeah, so when you look at an equation like this or like this, and you ask what is the inverse of U, does it kind of pop out at you?
So if you do inverse for the first time, become UT inverse times U inverse, and
So the question was, if this equation holds, then what is U inverse?
I inverse is the same as itself, so it's I.
Right.
So inverse of that is just itself. Inverse of
Yeah, okay. So this is what I was looking for. So remember that when we talk about the inverse, we have this expression. This is one property of the inverse, right? If I take U and I multiply it on the right by U inverse, I must get identity. And then I have another property of the inverse that says if I take U and I multiply it on the left by the inverse, I also get the identity. Now if I compare this to this, what is the inverse of U? U transpose. That's it, right? U transpose. Okay, so this is, when you have an orthogonal matrix U, the inverse is just the transpose. Generally speaking, the inverse is something that is difficult to compute. It takes some effort. But in this case, all you have to do is transpose the matrix. It's super easy. But that only happens with orthogonal matrices.
So would you tell us in an exam that the matrix is orthogonal, or would we have to figure that out ourselves?
I mean, it depends on the question, right? If I want you, if I'm asking to see if you understand what orthogonality is, I could say, is this matrix orthogonal or not? Or I could say, we have an orthogonal matrix, simplify this expression. And then you would hopefully remember that this could be used to do the simplification. Okay, so those are orthogonal matrices. Generally speaking, when we multiply a vector by an orthogonal matrix, what it does is it just rotates it. Actually, I'll talk about that in a moment. Any questions on anything on this page? Okay, so let's talk about some operations. So we first start with the norm. The norm, which is something that we write with this pair of double bars. If I say I have the norm of a vector, I'm telling you some description of how long that vector is, its length. And there's actually different ways to define norms. The ones we'll be using most in this class are the Euclidean or L2 norm, which is the usual way that we humans think about distance from one point to another. You just take the straight line between those points, and that would be the Euclidean norm. But there's other ways to define norms, and so if you do that, basically what you're doing is you're taking the square root of the sum of the squares of that vector. That's how the Euclidean norm is defined. It's also called the L2 norm sometimes. There's other ways to define distance, like this L1 norm. And sometimes that's a better way. So if you're a taxi driver in Manhattan and you need to pick someone up and you can only drive down a street and make a left and drive down another street, you measure different distance in a different way. So for example, if I'm here, let's say, if this is the origin, that's where I start, and I want to get to this location here, and I'm the taxi driver, I would measure distance as this distance plus this distance. If I'm a crow and I can fly directly, I would measure distance like this, right? Both are valid notions of distance, it just depends who you are. So that taxi cab distance is this. You can see that's the sum of the absolute value of every component. So it's the absolute value of this plus the absolute value of this. So these are different notions of distance, they're both norms. If no norm is specified, we always assume the Euclidean one. So if you ever see an expression like x without any subscript telling that it's Euclidean or not, then you assume it's Euclidean. And now getting to this property I was going to tell you about before, if you have an orthogonal matrix, another interesting interpretation of them is that they preserve distance, they preserve length, at least in the Euclidean sense. So that means orthogonal matrices, they just rotate vectors. They do not stretch vectors. If you think about a matrix as like an operation on a vector, it just rotates a vector, it doesn't change its length. Okay, any questions on norms? Okay. Another thing we'll use a bunch is the trace. The trace is just the sum of the diagonal elements of a square matrix. So in terms of an expression, let's say I have a matrix A sub II, that would be the ith diagonal element, and I'm just going to sum them all. So in this case, I'm assuming that the matrix A is n by n, because I'm summing n elements. There's two key properties of the trace. The first is it's a linear operation. That means that if I have any scalars alpha and beta, and I have any two matrices A and B, the trace of alpha A plus beta B is, let me see. Let's see, is Claire Beinecke here?
Yes.
Okay. So if you remember linearity, maybe from some other courses, it kind of gives you a hint, the idea what this would be. No? Okay, so it's going to be alpha times the trace of A plus beta times the trace of B.
So like alpha and beta are just like scalars that you
Yes,
Okay.
they're scalars. And we know that because they are lowercase and bold, and non-bold. Yeah, so linearity is a concept I'll talk about a lot. This is an example of linearity. If it's not the trace but some other operation, and you want to say is that a linear operation or not, it's exactly this equation, but replacing trace with some other operation. It means that if you have a scaled sum of two inputs, basically scaling and summing at the input is the same as scaling and summing at the output. That's what a linear system does, or a linear operator. Okay, so that's one key property. The other property that we'll exploit a lot is almost a little bit counterintuitive. Remember how we said that with matrix multiplication, you cannot reverse the order. You cannot, if you have A times B, that's not the same thing as B times A. That's true, it's not the same. But when those things appear, that product appears inside a trace, it turns out you can swap them, and it will not change the value of the trace. So trace of A times B is the same as trace of B times A.
Is that because it's a square matrix? Is that how that works?
Well, A and B don't have to be square. Their product is square. But yeah, maybe that's one of the ways you can think about it. So A could be wide and B could be tall. And over here, if I swap them, notice that now B, the tall one, is on the left. Okay, so if on the left side I have something of that size, and on the right I have something much bigger. Right? So I'm just saying, for example, A could be wide, a wide matrix. B could be a tall matrix. in order to make this a legal multiplication, this dimension has to match this dimension. So let's just assume it does. And if that's the case, and you do this multiplication, you get something with this many rows and with this many columns. And that thing needs to be square to be inside a trace. Now, once I swap these, B, the tall one, moves to the front, A to the back, and now, yes, everything matches in dimension, but what's interesting is that their product is actually much bigger. It's the tall times the tall size. And so what this relationship says is that when you sum across those elements, you get the same value as when you sum across those elements. So it's pretty interesting, and it's very useful because sometimes we want to do that swapping, and we can make it happen inside a trace. Okay. Great. Any questions on this? Okay. Matrix inverse. So for any square matrix, when we talk about inverting a matrix, it has to be square. The inverse, if it exists, is a matrix such that when you multiply on the left or on the right, it basically cancels the original matrix in the sense that you get identity. But a key point to remember is that this inverse does not exist for all A. It's analogous to with real numbers. If I have the number 0, and I say, what's the inverse of 0? It's not a real number. It doesn't exist. You could say it's infinity, but that's not a real number. So similarly, this is sort of a generalization of that idea. You might have a matrix A. You're trying to invert it. There might not be any inverse. Okay. So if the inverse does exist, we say that A is invertible, or sometimes we'll say it's non-singular. If the inverse doesn't exist, we could say it's singular. Okay, so let's assume that the inverse of A exists. If we invert a matrix and then we invert the inverse, we get back the original matrix. If we have a product A times B, and let's say that they're both invertible, and we invert the product, similar to the way the transpose works, you invert the individual ones and you swap their orders. And finally, if you transpose A inverse, that's the same thing as inverting A transpose. A number of useful things. Generally speaking, for large matrices, the inverse is a very complicated thing. It's something done with an algorithm. It's not something you can easily write down. But with a 2x2 matrix, we can write it down. So what we're saying here is if A takes this form, A11, A12, A21, A22, then to compute the inverse, what you do is you swap those two diagonal entries like this, you negate the off-diagonal entries like this, and you divide by this thing, which is the product of the diagonals minus the product of the off-diagonals. When you do this, you get a matrix A inverse that when you multiply by A, everything gets canceled and you get this identity. Okay, that's something you could verify on your own. If you take this expression and you multiply by this and you work out the details, you will get the identity matrix. Okay, 2x2 case, we can write it down. It's relatively easy to do. Larger matrices, we tend to do this numerically with MATLAB or NumPy or something.
For the matrix in blue, shouldn't the bottom left be A21 and the top right be A12?
Yes. Sorry. Did it wrong. So we want row, column. Exactly. Yes, thank you. Okay, so that's the matrix inverse. Any questions on the inverse? Okay. It turns out that this thing down here is something called the determinant. The The determinant is something that has a nice interpretation. If you have a square matrix, the determinant is the volume of a certain set of linear combinations. So it goes like this. If you take these AIs to be the different columns in A, and you scale each of those AIs by some coefficient that is anywhere between 0 and 1, and then you sum all those things together, there's a whole bunch of different vectors V that you can build. So here's an example. So A1 turns out to be this. And so imagine that I'm taking all scalings of this between 0 and 1. So I get all kinds of vectors that look like that, or that, or that. And then simultaneously I have this A2, and I can do all kinds of scalings of A2. And I add those things together. I can create any point in this gray region. So that is this set S. It's the set of all sums of those two things of scalings between 0 and 1 of them. Now, if you look at the volume of that set, that is, or the area in 2D, that is the determinant of the matrix. Okay, so that's the interpretation. So in the 2 by 2 case, again, we have a nice simple expression. This is the determinant. That is exactly the thing that showed up over here. For the higher dimensional case, it's more complicated. We tend to compute it numerically. One thing that we might need to use sometimes is if you scale a matrix before taking its determinants, that's the same thing as taking the determinant first and scaling, but the scaling must be done according to the dimension of the matrix. Let me give you some intuition here. If I made A1 and A2 each twice as long, I would get that region, right? You can see that region is 4 times the area of the original one, because I doubled it, but there were 2 dimensions. So that 2 dimensions means I square that doubling. If it was a volume, if I had a 3rd dimension, then it's like, you can imagine how it's now going to be, the volume has cubed. Okay, so that's the matrix determinant. Any questions there? Okay. We have a little bit left, but it's already a couple minutes late, so I'll let you guys go. We'll finish this up and do a bit more, and then next time we'll also start on the first machine learning unit. See you guys then.